Welcome to Dark Cosmos Theory. Now, let's talk about something you've experienced every single second of your existence, yet probably never truly understood. Gravity, the phenomenon that anchors you to this planet, orchestrates the cosmic ballet of galaxies, and shapes the very fabric of existence itself. Here's what's going to fundamentally alter your perception of reality. Gravity isn't what you think it is. It's not some invisible rope yanking objects downward. It's something profoundly more elegant, more strange, and more beautiful than human intuition could have imagined. Think about your current moment. You're experiencing weight right now. Perhaps you feel a chair supporting you or the ground beneath your feet. For your entire life, you've been told this sensation exists because Earth's gravity pulls you downward. That understanding isn't entirely false, but it's incomplete in a way that conceals the universe's most astonishing secret. What you're actually feeling is something entirely different, something that will make you see reality through completely new eyes. Let's start with what humanity thought it knew. When Isaac Newton gazed upon falling objects in the 17th century, he recognized something revolutionary. The same principle governing an apple's descent also commanded the moon's orbit around Earth and our planet's journey around the sun. Before Newton's insights, philosophers believed celestial mechanics operated under entirely separate laws from earthly phenomena. Heaven and earth followed different rules. Newton shattered that division, unifying cosmic and terrestrial motion through elegant mathematics. His law of universal gravitation stated that every object in existence attracts every other object with strength proportional to their combined masses and inversely proportional to their separation squared. Picture what this means. You and Earth pull on each other intensely because our planet possesses enormous mass. You and a book across the room also attract each other, but so feebly that you'd never detect it. The gravitational attraction between two people standing a meter apart equals less than the weight of a single microorganism. Gravity ranks as the weakest force in nature by staggering margins. Electromagnetic forces overpower gravitational attraction by 39 orders of magnitude at everyday scales. This represents one of physics' most profound unsolved mysteries. The inverse square law creates fascinating consequences. Double your distance from an object, and gravitational strength doesn't merely halve, it plummets to 1/4. Triple the separation and it crashes to 1/9. This mathematical relationship explains why gravity dominates only when masses become truly colossal, like stars and planets. Newton's equations performed magnificently. They predicted planetary motion with stunning accuracy. They explained ocean tides, those rhythmic risings and fallings caused by the moon's gravitational influence on Earth's waters. They revealed why distant planets crawl more slowly through their solar orbits. They even enabled the discovery of previously unknown worlds. Neptune's existence was confirmed in 1846 when astronomers noticed Uranus wasn't moving precisely as Newton's mathematics predicted. They calculated where an undiscovered planet must reside to create those orbital irregularities. Telescopes pointed toward that predicted location revealed Neptune exactly where the equations said it should be. Mathematical prophecy made manifest. For 2 centuries, Newton's framework seemed like the final word on gravity, but tiny problems lingered. The most famous involved Mercury's orbit. Mercury travels an elliptical path that slowly rotates over time, a phenomenon called precession. Newton's equations predicted how much Mercury should precess based on other planets' gravitational influences. Observations didn't match. Mercury was precessing 43 arcseconds more per century than predicted. That's roughly 1/18 of a degree per 100 years. Incredibly minute, yet undeniably real and precisely measurable. Scientists searched desperately for explanations. Perhaps an undiscovered planet called Vulcan lurked inside Mercury's orbit, tugging on it. Extensive searches found nothing. Maybe Newton's laws needed subtle adjustments. Every modification failed. The mystery persisted unsolved until 1915, when Albert Einstein unveiled his general theory of relativity. Einstein's revelation was radical beyond measure. Gravity isn't a force at all, it's the curvature of space-time itself. Those words probably sound like meaningless abstraction. Space-time curvature. What could that possibly mean? Let me build your understanding step by step, starting from concepts already familiar to you. Consider space and time as you normally conceive them. Space forms a three-dimensional stage where events unfold. You move forward and backward, left and right, up and down. Those constitute your three spatial dimensions. Time seems fundamentally different. It flows unidirectionally from past toward future. You experience events sequentially. You cannot rewind time or arbitrarily leap forward. Space and time appear categorically distinct. Space represents where things happen. Time represents when they happen. Einstein demonstrated that space and time aren't separate entities. They're woven together into a unified four-dimensional fabric called space-time. This isn't merely mathematical convenience. It's a description of physical reality. You cannot have space without time, or time without space. They're aspects of the same fundamental thing. When you move through space, you simultaneously move through time. When time passes, you're also moving through space-time. Even sitting motionless in space, you're still traveling through space-time at the speed of light, just entirely in the time direction. Here's where reality becomes truly fascinating. Space-time isn't rigid. It's flexible. It can bend and curve. What causes this curvature? Mass and energy. Any object possessing mass or energy curves the space-time surrounding it. Greater mass means stronger curvature. Earth curves space-time around itself. The Sun curves space-time far more dramatically because it's vastly more massive. Even you curve space-time by a minuscule amount. Everything with mass or energy warps space-time to some degree. Imagine space-time like a stretched rubber sheet. Place a bowling ball on it, and the sheet develops a depression. Heavier balls create deeper depressions. Roll a marble near the bowling ball, and it won't travel straight. It curves toward the bowling ball, following the depression's slope. From the marble's perspective, it's simply following the straightest available path. But because the sheet is curved, that path appears curved to outside observers. Similarly, Earth curves space-time around itself. When you drop a ball, it isn't being pulled by some mysterious force. It's following the straightest possible path through curved space-time. That path happens to curve toward Earth's center. You're not being pulled downward. You're attempting to follow your natural path through curved space-time, and the ground prevents you from doing so. The rubber sheet analogy has limitations. It's a two-dimensional surface bending in a third dimension. But space-time is four-dimensional and doesn't bend into some higher dimension. It's intrinsically curved, meaning the curvature exists as a property of space-time itself, not a distortion into something else. Also, the rubber sheet analogy uses gravity itself to make the ball sink, which creates circular reasoning when explaining gravity. Use the analogy for visualization, but recognize its boundaries. What does space-time curvature actually mean? The rules of geometry change. In flat space, the shortest distance between 2 points is a straight line. In curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, paths representing the shortest distance between 2 points in that curved geometry. On Earth's curved surface, the shortest path between two cities isn't a straight line through the air if you must stay on the surface. It's a curve following what's called a great circle route. Flights from New York to Tokyo arc over Alaska. On a flat map, this looks bizarrely curved. On a globe, it's actually the shortest route. In curved spacetime, objects follow geodesics. A planet orbiting the Sun isn't being pulled by any force. It's following a geodesic through the curved spacetime created by the Sun's mass. From the planet's perspective, it's moving in a straight line. But because spacetime is curved, that straight line looks like an orbit from our viewpoint. The planet continuously falls toward the Sun while moving sideways fast enough to keep missing it. Perpetual freefall. This explains astronaut weightlessness in orbit. They're not beyond Earth's gravity. At the International Space Station's altitude, roughly 400 kilometers above Earth's surface, gravitational field strength remains about 90% as strong as ground level. Astronauts feel weightless not because gravity disappeared, but because they're in freefall. They're following a geodesic through curved spacetime. Earth curves space-time, and the station follows that curvature, constantly falling toward Earth while moving sideways fast enough to perpetually miss it. Astronauts inside fall at identical rates as the station, so relative to the station they float. You experience this same phenomenon when jumping. During those brief airborne moments, you're in freefall. You're weightless. You don't feel weight pressing on your feet. The moment passes too quickly to truly notice. But if you could somehow extend that moment, remove the ground so you kept falling indefinitely, you'd feel exactly what astronauts experience in orbit. True weightlessness. Einstein's equivalence principle states a profound truth. These two situations are indistinguishable. Freefall in a gravitational field and floating in deep space with no gravity. You cannot tell the difference from inside your reference frame. Similarly, standing in an elevator on Earth feels identical to being in a rocket accelerating through deep space at 9.8 meters per second squared. From inside, no experiment can distinguish between standing on Earth and accelerating in space. These situations are equivalent. The equivalence principle generates remarkable predictions. One is gravitational time dilation. Time passes at different rates depending on your position in a gravitational field. Stronger gravitational fields mean slower time passage. Stand on a massive planet's surface where space-time is highly curved, and time passes more slowly for you than for someone in orbit, where space-time is less curved. This isn't perceptual. Time actually passes at different rates. Two synchronized clocks, one on the surface and one in orbit, will show different times when reunited. The surface clock will have recorded less elapsed time. This has been measured experimentally many times. In 1971, scientists placed atomic clocks on commercial airplanes and flew them around the world. Upon landing, those clocks ran ahead of identical clocks that remained on the ground by exactly the amount general relativity predicted. The difference was tiny, measured in nanoseconds, but real and measurable. GPS satellites must account for time dilation or their position. Calculations would be off by kilometers within hours. Atomic clocks on GPS satellites run slightly faster than ground-level clocks because they're higher up where space-time is less curved. The GPS system automatically corrects for this. Every time you navigate with your phone, you're relying on Einstein's predictions being accurate to within billionths of a second. General relativity also predicts gravitational lensing. Light follows geodesics through curved space-time just like everything else. When light passes near massive objects, its path curves. Massive objects can act like lenses, bending light that passes nearby. This was first observed during the solar eclipse of 1919. Astronomers photographed stars near the Sun during the eclipse when solar glare didn't overwhelm starlight. Stars appeared slightly displaced from their known positions. The Sun's gravity was bending starlight passing near it, making stars appear in slightly different positions. The displacement matched Einstein's predictions precisely. This observation made Einstein world famous overnight. Today, gravitational lensing is a standard astronomical tool. When light from distant galaxies passes near massive objects like galaxy clusters, between us and those distant galaxies the light gets bent. Sometimes light takes multiple paths around the massive object and we see multiple images of the same distant galaxy, or the galaxy gets stretched into arcs or rings. By studying these lensed images, astronomers map mass distribution in the lensing object, including dark matter, which we can't see directly, but which still curves spacetime. Black holes represent the most extreme example of curved spacetime. A black hole is a region where spacetime is so severely curved that nothing, not even light, can escape. The boundary of no return is called the event horizon. Cross it and all possible paths through spacetime lead inward toward the center. There's no way out, not because something pulls you in, but because spacetime itself is curved so extremely that all geodesics point inward. Black holes form when massive stars collapse at the end of their lives. A star balances between gravity, trying to compress it, and pressure from nuclear fusion pushing outward. As long as the star fuses hydrogen, helium, or heavier elements in its core, that pressure prevents collapse. Eventually, massive stars exhaust their fuel. Fusion stops. Outward pressure vanishes. Gravity wins. The star collapses catastrophically. If the star is massive enough, more than roughly 20 solar masses, the collapse doesn't stop. The entire star compresses into an infinitely small point called a singularity. Around that singularity exists the event horizon. The event horizon's size depends on mass. For a solar mass black hole, the event horizon would be about 3 kilometers in radius. That's called the Schwarzschild radius, after Karl Schwarzschild, who calculated it in 1916, just months after Einstein published general relativity. For a 10 solar mass black hole, the radius would be roughly 30 kilometers. For a supermassive black hole with 1 billion solar masses, like those at galaxy centers, the radius would be nearly 3 billion kilometers, larger than Saturn's orbit. This bends people's minds. From the perspective of someone falling into a black hole, they cross the event horizon in finite time. They'd fall through in seconds or minutes or hours, depending on the black hole's mass. But from an outside observer's perspective, the falling person never quite reaches the event horizon. As they approach, time dilation becomes increasingly extreme. Time passes slower and slower for the falling person relative to the outside observer. Light from the falling person becomes increasingly redshifted, shifting from visible light to infrared to radio waves, becoming dimmer and dimmer. Eventually, they appear to freeze just outside the event horizon, fading from view. But this is just a perspective effect. The person experiences themselves falling through normally. Inside the event horizon, spacetime is so warped that the future points toward the center. Just as surely as your future in normal spacetime points forward in time, your future inside a black hole points toward the singularity. You can no more avoid hitting the singularity than you can avoid moving forward in time. The singularity isn't a place in space you can dodge by moving sideways. It's a moment in your future that you will inevitably reach. At the singularity, space-time curvature becomes infinite. Matter compresses to infinite density. Our current theories break down. General relativity predicts the singularity, but can't describe what happens there because the mathematics produces infinities, which usually signals the theory has reached its limits. Most physicists think quantum effects, which general relativity doesn't include, become important before reaching the true singularity. But we don't have a complete theory of quantum gravity yet, so we can't say for certain what happens at a black hole's very center. There's widespread misconception about black holes. People think they're cosmic vacuum cleaners, sucking in everything around them. Not true. A black hole only pulls on things gravitationally, just like any other massive object. If our sun suddenly became a black hole with the same mass, which it won't because it's not massive enough, Earth's orbit wouldn't change. We'd still orbit at the same distance. We'd freeze because the sun wouldn't radiate light and heat anymore, but we wouldn't get sucked in. You only get into trouble with a black hole if you venture very close, closer than you could approach a normal star because the star's physical surface would be in the way. With a black hole, the physical matter has collapsed inside the event horizon, so you can get much closer to the center of mass. That's when tidal forces become extreme. Tidal forces are differences in gravitational pull across an object. Earth's tides are caused by the Moon pulling slightly harder on the side of Earth facing it than on the opposite side. With normal objects like Earth or the Moon, tidal forces are gentle. But near a black hole, they become savage. If you fell feet first toward a black hole, your feet would be closer to it than your head. The pull on your feet would be stronger. The difference would stretch you. As you got closer, the stretching would become increasingly extreme. Eventually, you'd be pulled apart, stretched like spaghetti. Physicists call this spaghettification, a real term used in technical papers. For a small black hole, spaghettification would happen before you even reach the event horizon. For a supermassive black hole, the event horizon is so far from the center that tidal forces at the horizon are relatively gentle. You could cross the event horizon without immediately being torn apart. You'd only get spaghettified much later. As you fell closer to the singularity, black holes aren't completely black. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon, now called Hawking radiation. The basic idea is that empty space isn't truly empty. Quantum mechanics tells us that particle-antiparticle pairs constantly pop into existence and then annihilate each other almost immediately. Normally, this doesn't lead to anything observable. But near a black hole's event horizon, one particle might fall into the black hole while the other escapes. From outside, it looks like the black hole is emitting radiation. This radiation carries energy away from the black hole, so the black hole gradually loses mass and shrinks over time. Black hole evaporation. The effect is incredibly slow for large black holes. A solar mass black hole would take approximately 10 to the 67th years to evaporate. For comparison, the universe is only roughly 13.8 billion years old, so a solar mass black hole would take vastly longer than the current age of the universe to evaporate. For supermassive black holes, evaporation time is even longer, far beyond any meaningful timescale. Gravitational waves are one of the most spectacular confirmations of general relativity. According to Einstein's theory, accelerating masses produce ripples in spacetime itself. These ripples travel outward at the speed of light, carrying energy away from their source. Imagine throwing a rock into a pond. Ripples spread across the water's surface. Gravitational waves are similar, except they're ripples in the fabric of space-time itself. As a gravitational wave passes through a region of space, it alternately stretches and squeezes that space in perpendicular directions. Einstein predicted gravitational waves in 1916, but thought they'd be far too weak to ever detect. For decades, they remained purely theoretical. Then in the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. They observed that the orbit was gradually decaying. The two stars were slowly spiraling inward. The rate of decay matched exactly what you'd expect if the system was losing energy to gravitational waves. Indirect evidence that gravitational waves exist. Hulse and Taylor won the Nobel Prize for this discovery. But detecting gravitational waves directly required building incredibly sensitive instruments. In the United States, scientists built LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two facilities, one in Louisiana and one in Washington state, separated by 3,000 kilometers. Each facility has two arms 4 kilometers long, arranged in an L shape. Laser beams bounce back and forth along these arms. If a gravitational wave passes through, it stretches space in one direction and squeezes it in the perpendicular direction. The change in distance is incredibly small. When LIGO made its first detection, the change was roughly 1/10,000th the diameter of a proton, like measuring the distance to the nearest star to within the width of a human hair. The precision required is almost incomprehensible. On September 14, 2015, both LIGO detectors picked up a signal. A gravitational wave had swept through Earth. By analyzing the signal, scientists determined it came from two black holes, 29 and 36 times the mass of our Sun, spiraling into each other 1.3 billion light-years away. As the black holes orbited each other, they emitted gravitational waves, losing energy and spiraling inward faster and faster. In the final fraction of a second, they merged, creating a single black hole 62 times the mass of our Sun. Wait a minute. 29 plus 36 equals 65, not 62. What happened to those three solar masses? They were converted entirely into gravitational wave energy, according to Einstein's equation E equals mc squared. In a fraction of a second, this merger released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. The power output during that brief moment was roughly 50 times the combined power output of all stars in the universe. Hard to wrap your mind around that, since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are black hole mergers, but some are neutron star mergers. In 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding. This event was also observed with traditional telescopes across the electromagnetic spectrum from gamma rays to radio waves. The first time an astronomical event was observed with both gravitational waves and light. This ushered in a new era of multi-messenger astronomy where we study cosmic events using different kinds of signals. What makes gravitational wave astronomy revolutionary isn't just detecting these events, it's what we learn from them. When neutron stars merge, the gravitational wave signal encodes information about their internal structure. Neutron stars are laboratories for extreme physics, with matter compressed to densities where atomic nuclei merge into exotic states. Different theories about how matter behaves under these conditions predict slightly different gravitational wave signatures during a merger. By analyzing the waves, we're essentially probing the interior structure of neutron stars, conducting experiments on matter at nuclear densities that we could never achieve on Earth. These observations also test fundamental physics. The speed of gravitational waves equals the speed of light to extraordinary precision. This wasn't guaranteed by theory. Some alternative theories of gravity predict different speeds. The LIGO-Virgo observations constrain or rule out entire classes of modified gravity theories. Every detection is simultaneously a discovery and a test, building confidence in general relativity while searching for any deviation that might point toward new physics. Gravitational waves also offer a unique way to measure cosmic distances. The amplitude of the wave tells us how far away the source is, while the frequency evolution tells us the masses of the merging objects. If we can also identify the host galaxy with traditional telescopes, we can measure both the distance and the galaxy's recession velocity. This gives us an independent measurement of the universe's expansion rate, potentially resolving current tensions between different measurement methods that give slightly different results. In the coming decades, even more sensitive gravitational wave detectors will be built. LISA will consist of 3 spacecraft arranged in a triangle with sides 5 million kilometers long. It will detect lower frequency gravitational waves from sources like supermassive black holes merging at the centers of galaxies, events LIGO can't detect because it's designed for higher frequencies. These cosmic collisions release energy that staggers the imagination, warping spacetime across entire galactic volumes. Dark matter and dark energy have puzzled scientists for decades. When astronomers study galaxies, they measure how fast stars orbit the galactic center. Based on visible matter, stars on the outer edges should move much slower than they do. The only explanation is additional mass we can't see, providing extra gravitational pull. We call this dark matter. It doesn't emit light or any electromagnetic radiation. That's why it's dark. But it has mass, so it curves space-time and affects visible matter through gravity. Roughly 85% of the matter in the universe is dark matter. Only 15% is ordinary matter that makes up stars, planets, and people. What is dark matter? We don't know. It's not just dark clouds of normal matter like planets or dust, because such objects would absorb and block light from objects behind them. Dark matter doesn't do that. It's completely transparent. Leading theories suggest it's made of undiscovered subatomic particles that don't interact with light or normal matter except through gravity. Scientists are building detectors deep underground to try to catch dark matter particles colliding with normal atoms. So far, they haven't detected anything conclusive. The search continues. The evidence for dark matter goes beyond galactic rotation curves. When astronomers study galaxy clusters, they find the same problem magnified 1,000-fold. The visible matter in these clusters, all the stars in all the galaxies combined, accounts for only a small fraction of the total mass needed to hold the cluster together. The hot gas between galaxies adds more mass, but still not enough. Dark matter makes up the bulk of the cluster's mass, creating the deep gravitational well that holds everything together. Gravitational lensing provides another independent confirmation. When light from distant galaxies passes through galaxy clusters, it gets bent by the cluster's gravity. By measuring how much the light bends, astronomers can map the total mass distribution, including dark matter. These maps reveal that dark matter forms massive halos around galaxies, extending far beyond the visible stars. The dark matter halo around our Milky Way extends roughly 600,000 light-years from the galactic center, dwarfing the visible galaxy itself. Dark matter's gravitational influence shaped the universe's large-scale structure. In the early universe, dark matter clumped together first, creating gravitational wells that attracted ordinary matter. Stars and galaxies formed inside these dark matter scaffolds. Without dark matter's gravity, galaxies as we know them couldn't exist. The universe would be a very different place, perhaps just a thin soup of gas that never condensed into stars and planets and life. Dark energy is even more mysterious. In 1998, astronomers studying distant supernovae made a shocking discovery. The universe's expansion is accelerating, completely unexpected. After the Big Bang, the universe started expanding. Everyone assumed gravity would gradually slow that expansion over time, but acceleration suggested something was pushing the universe apart, counteracting gravity. This mysterious something is called dark energy. It appears to be a property of space itself. As the universe expands, creating more space, there's more dark energy. This drives faster expansion, which creates even more space and even more dark energy. A runaway process. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter is around 27%. Ordinary matter is approximately 5%. We live in a universe where 95% of it is stuff we don't understand. The existence of dark energy has profound implications for the universe's fate. Because the expansion is accelerating, distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away so fast that their light can no longer reach us. In the far future, trillions of years from now, the universe will be a much lonelier place. Most galaxies will be beyond our cosmic horizon. Only the galaxies in our local group, held together by gravity into a single structure, will remain visible. Cosmology is the study of the universe as a whole. General relativity describes not just gravity, but the structure and evolution of the entire universe. In 1922, Alexander Friedmann used Einstein's equations to show that the universe must be either expanding or contracting. It can't be static. Einstein initially resisted this, believing the universe was eternal and unchanging. Then in 1929, Edwin Hubble observed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. This proved the universe is expanding. Space itself is stretching, carrying galaxies apart. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward far enough, and everything was compressed into an incredibly hot, dense state. The Big Bang. Not an explosion in space, but the expansion of space itself. Evidence is overwhelming. First, galaxies are moving apart. Second, the universe is filled with microwave radiation called the cosmic microwave background, the afterglow of the Big Bang from when the universe was only around 380,000 years old. Third, the abundances of light elements match predictions. In the first few minutes after the Big Bang, nuclear fusion created hydrogen, helium, and traces of lithium. The ratios we measure today match the predictions precisely. The Big Bang theory says the universe had a beginning roughly 13.8 billion years ago. Before that, there was no before in any meaningful sense because time itself began with the Big Bang. Asking what came before the Big Bang is like asking what's north of the North Pole. A meaningless question. Time is part of the universe, part of space-time. When space-time began, time began. There was no earlier time. The cosmic microwave background radiation provides us with a baby picture of the universe. When the universe was 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, free electrons scattered photons constantly, making the universe opaque like fog. After recombination, photons could travel freely. Those ancient photons, stretched by cosmic expansion into microwave wavelengths, still fill the universe today. Every direction we look, we see this ancient light, the oldest light that can exist, the cosmic microwave. Background has a temperature of 2.7 Kelvin, incredibly uniform across the sky. But tiny fluctuations exist, temperature differences of only a few millionths of a degree. These fluctuations represent density variations in the early universe, the seeds that would grow into galaxies and galaxy clusters. Gravity amplified these tiny differences. Slightly denser regions had slightly stronger gravity, pulling in more matter, becoming denser still, pulling in even more matter. Over billions of years, this process created the cosmic web of structure we see today. The patterns in the cosmic microwave background encode enormous information about the universe's properties. By analyzing these patterns in exquisite detail, cosmologists have measured the universe's age, its geometry, its composition, and its expansion history with remarkable precision. The data tell us the universe is spatially flat to within measurement error. They tell us ordinary matter makes up only 5% of the total energy density. They tell us dark matter and dark energy dominate. They tell us the universe will expand forever, accelerating eternally into a cold, dark future. Experimental tests have confirmed general relativity in increasingly extreme conditions. The first test was the deflection of starlight during the solar eclipse of 1919. According to Newton, light shouldn't be affected by gravity because light has no mass. But according to Einstein, light follows geodesics through curved spacetime. The sun curves spacetime, so light passing near it should have its path bent. Arthur Eddington led expeditions to observe the eclipse from two locations, Sobral in Brazil and Principe, an island off West Africa. The idea was to photograph stars near the sun's disk during the eclipse and compare their positions to their known positions when the sun wasn't nearby. If Einstein was right, stars should appear displaced because their light had been bent by solar gravity. The results showed displacement of approximately 1.8 arcseconds for light grazing the solar surface, less than 1/12,000th of a degree, but measurable and matching Einstein's predictions. This made front-page news worldwide. Einstein became a celebrity overnight. The New York Times headline read, "Lights all askew in the heavens." Since then, gravitational lensing has been observed countless times with far greater precision. Modern telescopes routinely see lensed images of distant galaxies bent into multiple images or arcs by galaxy clusters in the foreground. We use gravitational lensing as a tool to map the distribution of mass, including dark matter, in those clusters. Some of the most distant galaxies ever observed are only visible because intervening mass concentrations magnify them gravitationally, acting as natural telescopes billions of light-years across. Another key test was Mercury's perihelion precession. When Einstein completed general relativity in 1915, one of the first things he did was calculate Mercury's orbit. General relativity predicts that space-time curvature near the Sun causes extra precession. When Einstein calculated the amount, he got exactly 43 arcseconds per century, the decades-old mystery solved in an instant. Einstein later said this was one of the happiest moments of his life. Gravitational redshift provides another crucial test. Light climbing out of a gravitational well loses energy. For light, energy is related to frequency. Lower energy means lower frequency and longer wavelength. For visible light, this shifts the color toward the red end of the spectrum. First measured in 1960 using the Moosbauer effect, a technique that allows extremely precise measurements of frequency. Scientists put a radioactive source at the top of a tower and a detector at the bottom. The gamma rays emitted by the source were slightly redshifted by the time they reached the detector, exactly as general relativity predicted. Light from the sun shows a small but measurable redshift compared to laboratory sources. From white dwarf stars, the redshift reaches approximately 50 parts per million. From neutron stars, light is redshifted by around 30%. Near a black hole's event horizon, photons climbing out lose so much energy that the redshift becomes enormous. Light barely escaping the horizon shifts to infinitely low frequencies. Time dilation has also been measured using extremely accurate atomic clocks. In 2010, scientists at the National Institute of Standards and Technology showed they could detect time dilation over a height difference of just 33 centimeters. They placed two atomic clocks, one 33 centimeters higher than the other. The higher clock ticked slightly faster because it was in a slightly weaker gravitational field. The difference was only around 90 trillionths of a second per day, but it was measurable. This stunning precision shows that general relativity holds even for tiny differences in gravitational potential. General relativity has been tested in many ways over the past century, and it's passed every test with flying colours. But we know it's not the final theory. It's incompatible with quantum mechanics, our other fundamental theory. Quantum mechanics describes the microscopic world of atoms and particles. General relativity describes the macroscopic world of stars and galaxies. Both theories work brilliantly in their respective domains. But when you try to apply both to the same situation, like the interior of a black hole or the first instant of the Big Bang, they give contradictory answers. Before we explore that incompatibility further, there are other predictions of general relativity worth examining. One is frame dragging. A massive rotating object drags spacetime around with it as it spins. Picture a ball of honey rotating in a bowl. The honey near the ball gets pulled along with the rotation. Spacetime behaves similarly near rotating masses. The effect is incredibly small for objects like Earth, but it has been measured. In 2004, NASA launched Gravity Probe B, a satellite carrying 4 ultra-precise gyroscopes. These gyroscopes were so perfectly spherical that if you scaled them up to the size of Earth, the tallest mountains would be only around 2 meters high. The satellite orbited Earth for over a year, measuring tiny changes in the gyroscope's orientations caused by frame dragging. The results confirmed Einstein's predictions. Earth's rotation drags spacetime around with it, and the gyroscopes detected that drag. The effect was minuscule, about 41 thousandths of an arc-second per year, but real and measurable. Frame dragging is much more significant near rapidly rotating black holes. A black hole can have 3 properties: mass, electric charge, and angular momentum, which means it's spinning. Most black holes probably have little to no charge because charge tends to attract opposite charges and neutralize. But angular momentum is different. If a star is rotating when it collapses, and all stars rotate at least a little, the resulting black hole will be spinning. A spinning black hole drags spacetime around it in a vortex. This creates an ergosphere, a region outside the event horizon where spacetime is being dragged around so forcefully that nothing can remain stationary. You'd have to move along with the rotation just to stay in place relative to distant stars. In principle, you could extract energy from a rotating black hole using a process called the Penrose process. You drop an object into the ergosphere. The object splits into 2 pieces. One piece falls into the black hole, carrying negative energy from the black hole's perspective. The other piece escapes with more energy than the original object had. The black hole loses angular momentum and slows down. You've extracted rotational energy from the black hole. This might sound like science fiction, but it's a legitimate consequence of general relativity. Whether any civilization could actually accomplish this in practice is another question. Some theoretical physicists suggest that highly advanced civilizations might harvest energy from rotating supermassive black holes at the centers of galaxies, using them as cosmic power plants. If such civilizations exist, their energy signatures might be detectable as anomalous emissions from galactic cores. Another fascinating prediction involves closed time-like curves, which are paths through space-time that loop back on themselves, allowing travel into the past. In certain solutions to Einstein's equations, like the Gödel metric and rotating wormholes, these paths exist. You could in principle travel along such a path and arrive at an earlier time. This raises all the problems with time travel, like paradoxes. If you went back in time and prevented your own birth, would you still exist to go back? General relativity doesn't forbid closed time-like curves, but most physicists think they're impossible for other reasons. Perhaps quantum mechanics prevents them. Perhaps the conditions needed to create them are physically unrealizable. Or perhaps they exist, but information or objects traveling through them would be destroyed by quantum effects. We don't know. It's an open question that touches on deep issues about causality, determinism, and the nature of time itself. We need a unified theory of quantum gravity. String theory and loop quantum gravity are leading candidates, but neither is confirmed. Until we have a complete quantum theory of gravity, there will be aspects of the universe we can't fully understand. Despite this, general relativity remains one of the most successful theories in science. It has revolutionized our understanding of the cosmos. It predicted black holes, gravitational waves, the Big Bang, and much more, all of which have been confirmed. Consider what this means for you personally. You're not held to Earth by an invisible force pulling you down. You're following the natural contours of curved space-time. The ground exerts electromagnetic forces that resist your body's natural tendency to move along a geodesic through space-time. What you interpret as weight is actually the sensation of this resistance. If the floor suddenly vanished and you started falling, you'd feel weightless, not because gravity stopped, but because you're now free to follow your geodesic. When you look up at the night sky, you're seeing objects separated by vast distances, but you're also seeing the past. Light takes time to travel. The light from our sun is 8 minutes old when it reaches you. Light from the nearest star is over 4 years old. Light from distant galaxies is billions of years old. You're literally looking back in time. The universe has a history written in light, and that light has been traveling through curved space-time to reach your eyes. You're also part of this cosmic story. The atoms in your body were forged in stars billions of years ago. Those stars exploded as supernovae, scattering their atoms into space. Over eons, those atoms drifted, eventually coming together in a cloud of gas that collapsed under its own gravity to form our solar system. Earth formed from that material, and eventually, after billions of years of evolution, those atoms arranged themselves into you. You're made of stardust, not a metaphor, literally true. The carbon in your cells was created inside red giant stars through the triple alpha process, where 3 helium nuclei fuse into carbon. The oxygen you breathe was forged in the cores of massive stars shortly before they exploded. The iron in your blood was created during supernova explosions themselves, in the brief moments when collapsing stellar cores reach temperatures of billions of degrees. The calcium in your bones, the sodium and potassium that carry signals through your nerves, the phosphorus in your DNA, all were manufactured in stellar furnaces across billions of years. Those atoms have been on a cosmic journey. After being ejected into space by dying stars, they spent millions of years drifting through the interstellar medium, the thin gas between stars. Slowly, over time, they became part of a vast molecular cloud, a region where gas density increases enough for gravity to start pulling matter together. 4.6 billion years ago, something triggered the collapse of part of that cloud, perhaps a nearby supernova's shockwave or the gravitational influence of a passing star. As the cloud collapsed under its own gravity, it began to spin, flattening into a disk. The center became denser and hotter, eventually forming our sun. In the disk around the young star, dust grains stuck together, forming larger and larger clumps. Over millions of years, these clumps grew into planetesimals, then into planets. The atoms in your body were part of that process, incorporated into the rocky material that would become Earth. They've been cycling through Earth's geology and biosphere ever since, perhaps spending time as ocean water, or locked in rocks deep underground, or part of ancient life forms long extinct. Now they're part of you, arranged in the precise configuration that creates your consciousness, your thoughts, your experience of being alive. And they're all following geodesics through curved space-time, held together by electromagnetic forces, but guided by gravity's geometry. Your existence is temporary. Eventually those atoms will be recycled again, becoming part of other structures, other beings, continuing their cosmic journey. General relativity has profound implications for space travel and our potential future as a spacefaring species. Nothing can travel faster than light because the speed of light is the speed of causality, the speed at which information can propagate through spacetime. Anything with mass must travel slower than light. As you accelerate an object approaching light speed, the energy required to accelerate it further increases without limit. To actually reach light speed would require infinite energy, which is impossible. This creates severe constraints for interstellar travel. The distances between stars are measured in light years. Even traveling at close to light speed, it would take years to reach nearby stars. And due to time dilation, the faster you go, the less time you experience for the journey. If you could travel at 99% of light speed to a star 10 light years away, the trip would take just over 10 years from Earth's perspective. But you'd age only roughly 1.5 years due to time dilation. When you returned, you'd have aged 3 years, but more than 20 years would have passed on Earth. Everyone you knew would be older. Some might have died. You'd have travelled into their future. This is sometimes called the twin paradox. One twin stays on Earth, the other travels to a distant star at high speed and returns. When they reunite, the travelling twin is younger. This isn't a true paradox because the situations aren't symmetric. The travelling twin accelerated and decelerated, experiencing forces that the earthbound twin didn't. Acceleration breaks the symmetry. The mathematics of special and general relativity predict exactly how much each twin ages, and the predictions have been confirmed by experiments with particles and atomic clocks. The numbers become dramatic at extreme speeds. At 99.9% of light speed, time dilation becomes even more severe. A journey across the galaxy, 100,000 light-years as measured by observers at rest, would take roughly 100,000 years from Earth's perspective. But the traveller would experience only about 4,400 years passing. Still longer than human lifetimes, but vastly compressed compared to the external universe. This isn't science fiction speculation. The mathematics is straightforward, confirmed every day in particle accelerators, where subatomic particles moving at near light speed live much longer than their stationary counterparts before decaying. The universe imposes a cruel trade. Travel fast enough and you can reach distant destinations within a human lifetime from your perspective. But everyone you knew on Earth will be long dead when you arrive. You'd be traveling into Earth's future, emerging into a world centuries or millennia beyond your departure. There's no going back. General relativity tells us that space-time itself is dynamic, not a static stage on which events unfold, but an active participant. It curves in response to mass and energy. Those curves affect how matter moves, and that moving matter curves space-time in turn. A feedback loop. This dynamic interplay between matter and space-time gives rise to all gravitational phenomena we observe, from falling apples to black hole, mergers to the expansion of the universe itself. There's a deep philosophical implication too. In Newton's view, space and time were absolute. They existed independently of the matter and events within them. But Einstein showed this isn't true. Space-time is relational. It's defined by the events and objects within it. Take away all the matter and energy, and it's not clear that space-time would even exist in a meaningful sense. The universe is not a container with stuff inside it. The universe is the stuff and the relationships between the stuff. Space-time is those relationships. Where is gravitational physics headed? One exciting area is testing general relativity in even more extreme conditions. The Event Horizon Telescope is continuing to observe black holes, looking for any deviations from predictions that might hint at new physics. Future observations will track matter spiraling into black holes in real time, watching how space-time curvature affects the trajectories and emissions of doomed gas clouds. Scientists are particularly interested in measuring the photon ring, a bright, narrow band of light that orbits just outside the event horizon, completing multiple circuits before escaping to our telescopes. The exact structure of this ring encodes information about the black hole's spin and properties in ways that will test general relativity with unprecedented precision. Each photon in the ring has completed at least one full orbit around the black hole before reaching us, carrying information about space-time geometry in the most extreme environment accessible to observation. Gravitational wave detectors are becoming more sensitive. LIGO is being upgraded, new detectors are being built, and LISA, the Laser Interferometer Space Antenna, is planned for the 2030s. These will observe gravitational waves from a wider range of sources, giving us more opportunities to test general relativity and explore phenomena we can't study any other way. Future ground-based detectors may achieve sensitivities allowing them to detect continuous gravitational waves from rapidly rotating neutron stars, opening yet another observational window. The next generation of gravitational wave observatories will detect thousands of events per year rather than dozens. This flood of data will allow statistical studies of black hole populations, revealing how these objects form and evolve across cosmic time. We'll be able to trace the growth of supermassive black holes from the early universe to the present day, understanding how they shaped galaxy evolution and cosmic structure formation. Another frontier is the quest for quantum gravity. Several experiments are being designed to probe the interface between quantum mechanics and gravity. These are incredibly challenging because quantum gravitational effects are expected to be significant only at the Planck scale, approximately 10 to the minus 35 meters, 20 orders of magnitude, smaller than a proton. We can't build particle accelerators that reach those energies, but there might be subtle effects we can measure indirectly. Understanding gravity has practical technological implications. GPS is the most obvious example, but there are others. Gravitational wave detectors require developing laser systems, vibration isolation, and measurement techniques of extraordinary precision. These technologies spin off into other fields. Looking further ahead, some physicists speculate about manipulating space-time curvature for propulsion. If we could generate strong gravitational fields artificially, perhaps spacecraft could surf waves in space-time or create localized distortions that effectively move space around the ship rather than moving the ship through space. General relativity has fundamentally reshaped our understanding of the universe. Not just a better version of Newton's theory, but a completely different way of thinking about space, time, matter, and gravity. And it's been confirmed by every experiment and observation to date. One of the great intellectual achievements of humanity. One person, Albert Einstein, sitting and thinking, working out the implications of a few simple ideas, constructed a theory that describes the cosmos from the smallest scales we can probe to the largest structures we can observe. But the story doesn't end here. We know general relativity is incomplete. We're still searching for a deeper understanding that unifies it with quantum mechanics. We don't understand dark matter or dark energy, which make up 95% of the universe. We don't know whether the universe is finite or infinite, whether it will expand forever or eventually contract, whether there are other universes beyond our own. These are open questions. The universe still holds mysteries. What should you take away from all this? First, gravity isn't a force in the way you've been taught. It's the curvature of space-time. Objects follow geodesics through that curved space-time. When you feel weight, you're feeling electromagnetic forces preventing you from following your natural geodesic. Second, space and time are not separate. They're unified into space-time, and space-time is dynamic, curving in response to mass and energy. Third, general relativity has been confirmed by countless experiments and observations. From the precession of Mercury to the detection of gravitational waves to images of black hole shadows, Every test has supported Einstein's theory. Fourth, despite its success, general relativity is incomplete. It doesn't incorporate quantum mechanics. We need a theory of quantum gravity to fully understand the universe at its most fundamental level. Fifth, these ideas have practical applications beyond GPS. Gravitational lensing is a tool for astronomy. Gravitational waves are a new way to observe the universe. Understanding gravity helps us understand everything from star formation to the large-scale structure of the cosmos. And finally, there's something profound about understanding that you live in a universe of curved space-time. Every moment of your life, you're moving through space-time, following geodesics, experiencing time dilation relative to other observers, interacting with the curvature created by Earth and the Sun and the galaxy and all the mass energy in the universe. When you drop a ball and watch it fall, you're not seeing a force pulling it down. You're seeing it follow the natural geometry of space-time. When you look up at the moon, you're seeing an object in freefall, endlessly circling Earth, because that's the geodesic it follows through curved space-time. The universe operates according to these principles whether you understand them or not. But understanding them gives you a deeper appreciation for the reality you inhabit. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We're tiny creatures on a small planet, yet we've figured out fundamental laws governing cosmic scale phenomena. We've measured the curvature of space-time. We've detected ripples in that space-time from black holes colliding 1 billion light-years away. We've imaged the shadows of black holes at the centers of galaxies. We've traced the history of the universe back to fractions of a second after the Big Bang. This suggests that the universe is fundamentally knowable. The next time you think about gravity, don't think of it as a mysterious force pulling things down. Think of it as the shape of space-time. Think of yourself as moving through a four-dimensional geometry, following the contours of that geometry, experiencing its curvature. You're not standing still on a flat Earth with gravity pulling you down. You're accelerating upward through curved space-time held in place by electromagnetic forces from the ground. The ground is pushing you up constantly, preventing you from following your natural geodesic. Out there, in space, planets are following their geodesics around stars. Stars are following their geodesics around galactic centers. Galaxies are following geodesics through the larger scale curvature of cosmic space-time. Light from distant galaxies has been traveling for billions of years through expanding space-time, carrying information about the ancient universe. Gravitational waves from cataclysmic events ripple through space-time at the speed of light. Black holes sit in regions where space-time curvature becomes so extreme that not even light can escape. All of this is described by Einstein's equations. All of it follows from the idea that gravity is geometry. It's been over a century since Einstein published general relativity. In that time, it's been tested in countless ways. It's made predictions that seemed absurd but turned out to be true. It's survived every challenge. And it's given us a picture of the universe that's richer and stranger than anyone imagined. We live in a universe of curved space-time where black holes lurk in the centers of galaxies, where gravitational waves ripple across cosmic distances, where time passes at different rates depending on where you are, where the history of the cosmos is written in the light reaching us from distant sources. The universe, as revealed by general relativity, is beautiful, profound, and real. You're not just living in the universe. You're part of it, moving through curved space-time, following geodesics, experiencing the fundamental nature of reality itself. And that's the most remarkable thing of all.